Okay, we're going to conclude our discussion of security metrics by talking about three final metrics now. These are related to investment. We'll talk about first the return on security investment. We'll talk about net present value and internal rate of return. So the first metric of ROSI is pretty simple and only considers a fixed time interval, whereas net present value and internal rate of return allow us to consider investment over a longer time horizon. So what is return on security investment? Well, we've talked about costs and benefits of security, right? And sort of intuitively, if you want to think about what your return on security would be, you could compare the sort of the ratio between the net benefit you get from spending in security relative to whatever the cost of security is. And that's precisely what this ROSI equation and metric defines. So it's simply the benefit of security minus the cost of security divided by the cost of security. And you can sort of think of this as a ratio, which is why we can sort of see the relative costs and benefits shifting. So to make this a bit more formal in terms of our other metrics before, our ROSI is just the expected net benefit of security divided by the cost of security. And you can express that in terms of ALE if you want, like so, or ALE 0 minus ALES minus C over C. Now, ROSI is useful if you're trying to give a single scalar value that would communicate the return on investment that you get from security. And so ROI is something that people within the business community like to hear about, and it can be useful to measure. However, it has some drawbacks, one of which is that it just considers it for a single point in time. And in reality, investments often occur over longer periods of time, and you may have events at different periods of time. So we'll conclude by talking about two different metrics which actually consider the role of time in coming up with the measures. So the net present value, again, this is a standard measure used in finance, but we're sort of tweaking it for our special case in security. The net present value aggregates expected net benefit of information security over lots of periods into the future, and based on a discount rate that you provide, comes up with what the value of security is today. So it's given by this equation here, where you have you start by the C0, which is your one-off cost of how much you spend in security at time 0, plus then you sort of sum up the numerator there, and that sum is just expected net benefit, and it's divided by 1 plus r to the t. So what that is saying is r ends up being your discount rate, and so it's how much do you discount the future value of money based upon how far into the future the event occurs. And you can just sum this up potentially infinitely, so long as r is positive, then it should still converge. The other way to look at this, and still compute a metric that considers the effect of time, is to compute the internal rate of return, which is the discount rate. We'll call it R star, at which the decision maker who's using net present value becomes indifferent between making a security investment or not. So if you don't really have a set discount rate in mind, you can come up with a scalar value of what it is, how much you would have to discount future money in order to be indifferent between spending money on security or not. So again, higher values of R are better. So let's go through an example for each of these three metrics. And the example here is, let's say you're trying to counter a data breach. So you're in an organization who's considering whether to invest in a security mechanism that will reduce the likelihood of a data breach. And perhaps you're considering between two options which have different initial costs and recurring costs. So we're going to consider two simplified options. One is a data loss prevention technology, or often called DLP, which is basically a control you put in a network that will try to observe outgoing traffic and block things like social security numbers and credit cards from leaving your network. So it's a technology. It has a higher initial investment, but relatively low recurring costs. Once you've deployed the system, you have to pay for maintenance and maybe ongoing expenses. So we're going to set that as the initial investment is $15K, the recurring cost per year of $1K, and we think in this case about the expected loss. If you didn't make this investment, regardless of the two options, because if you're not making the investment, the baseline for comparison, we're going to say you'd expect to lose $5,000 because there's maybe a 25% chance that you would have to pay a $20,000 legal settlement. Now you can quibble with these numbers, but the point is to show the exercise. Now, for this system, suppose you're able to improve your expected loss for making the security investment to $2,000 per year. And the reason why you would still have losses here is that there's going to be false negatives, things get blocked that shouldn't be, and things that don't get blocked that should be. So that's one option. The other option is to forego the expensive technology, but instead just train your users to try to do the right thing, to not lose personal data, not be careless of personal data. So for that, user training option has a lower initial cost of say only $6K, but the recurring costs are higher, and that you have to periodically retrain your users, and you have to continue to do the training for it to be effective. But let's say if you do that, then it actually is more effective in terms of reducing the expected loss after making that investment. So we've got two security investment options, and we want to compute these metrics to try to identify which one makes more sense from an investment perspective. So we'll compute it for each of these metrics. Let's start with the expected net benefit of security, which is, again, doesn't really consider the effective time. But let's say, so the question here is which approach, the DLP versus training, is the better investment over 10 years using expected net benefit calculations over those 10 years. Expected net benefit is essentially the T-max, so you're going to be doing the same thing every year after year, and it's essentially T-max times the expected net benefit in each year, which is ALE 0 minus ALES minus the cost in that year. So you do that for each of the up to max years, and then you subtract out your initial outlay. So what you should do is do this calculation for both options, DLP and user training, and pause the video. Try to go back and look at your slides and write this out. And once you've done so and made the calculation, come back and press play again. Okay, so now you've made the calculation. I can show you the answer. For a DLP, we end up with something that looks like this. We have 10 years times 5 minus 2 minus 1K, which is 2K, minus 15K, which ends up with a net benefit of 5K. Compared to user training, it's 10 times 5 minus 1 minus 3 minus 6K. It ends up being 4K. So, by using the expected net benefit metric, both solutions provide value, but the data loss prevention provides more value. Now, but what would the other metrics say? So what is missing here, and what's been simplified in the expected net benefit calculation, is that you're considering $1 spent in year 10 is equally valuable to as $1 spent in year 0. And that may not be the case, and typically isn't, due to inflation, due to other sort of unforeseen changes that could occur over time. And so the net present value and internal rate of return calculations tackle that problem exactly. So what does net present value say? This is going to be a little bit hard for you to calculate on your own, but once we start discussing R very shortly, one of the first things we'll do is calculate these functions using R. But you could do it right now on a calculator if you wanted. So this is the net present value function. If we're going to assume a rate of return of 5% and a max of 10 years, then here's what the two outcomes look like. So for option 1, it's $15,000 initial outlay, sum from years 1 to 10. The expected net benefit each year, which is for option 1, is just $2,000 divided by this discount rate, and you compare that to the second case. And what you see here is that roles are reversed. Net present value of the user training actually is higher. So it contradicts what we saw with the expected net benefit calculation. Yeah. So you can get it. So it's worth noting off the bat that no single metric is necessarily going to always give you a consistent answer, but it depends what you value. So let's talk lastly about doing the same calculation for internal rate of return. So here we are basically solving for the R that ends up being break even. So you plug in all your numbers, and your denominators now is 1 plus R to the T. So you definitely would want to use an equation solver like what's possible in R to come up with the break-even calculations. To do break-even, you just take those equations and set it equal to 0 and find the value of R that matches that equation. And for DLP, the rate of return is 5.6%. For training, it's 10.5%. So by this token, it's actually considerably better than the training is considerably better than the DLP. So the way to interpret this is to say, if you have to borrow money, in order to fund your budget, user training remains a good investment, even if you're borrowing at a 10% interest rate. So it's like, in today's environment, that would suggest it continues to be valuable. Now, the last slide here is we will sort of visualize the continuum of possible values here for the different solutions for each of the cases. So option 1 is data loss prevention. So what we're plotting here on the x-axis is the discount rate. So if we vary the discount rate, that changes what our net present value is, which is what's on the y rate. So what this sort of makes sense is that as the discount rate gets higher and higher, your net present value goes down. And if you compare that to user training, then what you end up with is the line is a bit different because of the way the equation works. But we can already see a few things here. One is that net present value, as calculated for when we calculated the example, was at 5%. So the net present value for option 1 ends up being, like I said, about $400 and some dollars, with net present where it's higher for option 2. And then internal rate of return ends up being the point at which the lines pass through the value of 0. So, but what we can see here is that not only what are the circumstances in which option 2 is going to perform better. Essentially, it's everywhere, so long as the discount rate exceeds about 2%. Looks like it's only when the discount rate is very low does it make sense to invest in infrastructure. Okay, so that wraps up our discussion of security metrics. Thank you for your attention.